Hello, my name is Dr. Eric Landrum from the Department of Psychology at Boise State University, and you're watching the Research Methods screencast about hypothesis testing. And this really is one of those core topics, those core concepts in psychology, and especially for the researchers, because this is really the way that we frame our world and the way we make decisions about whether or not we have discovered new knowledge or have found a new insight about the world that we live in. So let's go ahead, dig in, and get started. Typically, what we've been doing here is that at the very beginning of most screencasts, we're kind of framing the conversation by suggesting and kind of reviewing some of the key concepts and terminology and definitions here. And I want to continue that. So, the research or working hypothesis is typically that assertion or that expectation as to what we expect to happen between variables or groups or the impact of the independent variable on the dependent variable. So, for instance, back a few screencasts ago, we talked about how my brilliant lectures combined with a textbook would lead to better student performance than just reading the textbook alone. That wording right there would be an example of the research or the working hypothesis. That's not technically the null hypothesis, and technically it's the null hypothesis that gets tested. Other working hypotheses might predict a certain difference that males outscore females or females outscore males on a certain type of psychological task. And so we're going to label the working hypothesis H sub 1 or H sub A for alternative. We use H sub 1 here because H sub 0 is what we're going to use the symbols for the null hypothesis. So if the null hypothesis were true, and remember, we're never going to prove that it's true because we don't ever prove anything, but if it were true, the differences between the treatment group and the control group, or what I've got here, the experimental group and the control group, are due to chance, which we can never rule out, plus the treatment effect. And so the notion, this would be the cleanest kind of conclusion we could draw. There is a whoppingly big difference between the two groups, and the only things that explain it are chance alone, which we're always going to have, and the treatment effect. The independent variable manipulation, it worked to improve something or decrease something or whatever the situation was. The null hypothesis is technically what we test when we conduct hypothesis testing. And so the null hypothesis, the generic version, is always going to be there's no effect of the independent variable on the dependent variable, or there's nothing going on, or there's no difference between the groups, or no relationship or association between the variables. And so the null hypothesis is actually what's going to be tested. Now, we're going to call it H sub 0, the 0 for the null. And most of the time, the strategy is to reject the null hypothesis. So I want to talk about the red and green buttons there at the bottom of the screen. I like this terminology, the reject and the accept, the red button, the green button. Technically speaking, though, you probably didn't learn it like this in your statistical methods class. You probably were taught reject and fail to reject, and that's exactly right. There's nothing wrong with that. I just think the verbiage is a little bit cumbersome. So I do like this simplification of reject and accept, but note that reject and fail to reject are probably a little bit more accurate and that's correct. But I think if you can make that translation in your head, accept and reject are a nice alternative way to think about it. The second point I wanted to make is that, we do have a bias in psychology as it's framed right now to work to reject the null hypothesis. It's really difficult to do this long and involved study, accept every hypothesis, and conclude we found nothing. Because when you accept the null hypothesis, that means that you didn't find anything. There were no differences, no associations that were significant. And we're coming up with our special use of that word significant here in a moment. However, having said that, there are times when no significant difference between groups or no relationship between variables might be very interesting. For example, if there's no relationship between one's age and their GPA, that could be really fascinating with regards to older students going back to school. If I found no difference between an Alzheimer's disease group and an age-matched, healthy, elderly matched control group on a memory performance task, well, that might be very fascinating that certain types of memories are preserved in Alzheimer's disease. Although technically that would be, accepting the null hypothesis. There's no significant difference. So the way psychology is framed for the most part these days is that we set up the null hypothesis and our goal is to knock it down. So it's kind of like that straw man. We set the pins up at the end of the bowling alley, but we want to knock them down at the end of the day. And so we attempt to reject it. That's typically our goal and our approach. So I mentioned already this very special term significant. And for us, the word significant is going to have a very specific statistical meaning. And so we don't want to throw around the word significant lightly. It's not the same as important or weighty or momentous or substantive. Significant means a statistical result has been reached. So, what is a significant difference? And I'm going to give you about 6 different translations of this. So, one of them hopefully will stick and you can wrap your head around it. A significant difference occurs, which is a result that's unlikely to be due to just random chance alone. It's a rare event if only chance were operating. So, if something is significant, odds are, and it's kind of like a 95% odds are, that that's not random. That difference is so large or that correlation is so huge that that just doesn't happen by random chance alone. Now, we can't conclude that it's the independent variable causing the relationship with the dependent variable, but we're going to try to rule out every plausible alternative explanation so that the only thing left standing by the notion of falsificationism is that it's our working hypothesis. We're never going to prove that our working hypothesis is true. But the goal is to disprove every other possible alternative explanation to the working hypothesis such that the only thing left standing, the only thing left that's reasonable and logical is what the working hypothesis asserts. And that's that notion of falsificationism. Again, I'm going to say this a bunch of different ways. We want the differences to exceed chance so much that we attribute the difference to the independent variable, and we're going to hope there are no confounding variables, none of those nuisance or extraneous variables. How rare does an experimental outcome have to be, assuming only chance is operating before the experimenter rejects the null hypothesis? It has to be pretty rare. How whopping, and I'm just joking here, it's really not a statistical term, but I like pretending like it is. How whopping do those differences have to be that something's going on there? That's not just random chance, but there's random chance plus some systematic effect or impact of the independent variables on the measurement of the dependent variable. And so we're looking for these big, huge, observable, easily identifiable differences. Now, we're not going to have to eyeball it. We're actually going to apply the statistical methods that we've learned in previous classes to actually make a decision about accepting or rejecting the null, concluding that there is a significant relationship or association or difference or not. So we decide the level of whoppingness ahead of time. That is, we, the researcher, that is those folks who are the hypothesis testers, we're going to determine the level of whoppingness. It's preset, and there are some pretty standard, typical cutoffs in psychology that we're going to use when we use this phrase significant difference. So usually we talk about a probability of 0.05, and what that means is that 95 times out of 100, we're going to assume equivalent groups in our experimental group and our control group. That is, random assignment worked. We know it's not perfect. We've talked about that in other screencasts. I don't want to really get back into that now. But we're just going to make the assumption that our research methods are pretty good and they work most of the time. And most of the time when we split from that sample into those two groups, it's relatively random. We're going to assume equivalent groups. But here's the thing. We're also going to assume, because we know it's not perfect, because we're dealing with human beings, because we know there are individual differences, we know there's chance, 5 times out of 100, we're going to assume that the groups were non-equivalent, that is different from the start, and that our results are still from chance, but we made an error. And we don't want to do this. See, here's the deal. We want the differences between the groups to be so huge that error alone is an unlikely singular explanation. We want these big whopping differences between groups so that it just can't be error. The odds of it being error by itself are minuscule. So 95 times out of 100, we're going to assume everything's kosher, random assignment worked. We've got equivalent groups. 5 times out of 100, we're going to admit though that our techniques are not perfect, and that's that 5 times out of 100 is that probability of same thing as 1 out of 20, 5%, a nickel out of a dollar. And sometimes we're going to conclude that's a big whopping difference, and we think it's the independent variable, but oh man, sometimes random assignment just doesn't work perfectly. So we can talk about the significance level as an amount of error we are willing to tolerate. And I like the little Snoop Dogg graphic there. If the p-value, and it really should be a lowercase p by the way, if the p-value is low, then the null must go. Okay, then the null must go. So just to recap, we know that random assignment is not a perfect technique and that occasionally by chance non-equivalent groups are formed. That is, the different already exists even before I start my study. What we determine ahead of time is to what degree this level of imperfection is tolerated. And I like that word tolerance. It's almost like, when nuts and bolts are manufactured in a factory, there's a certain level of tolerance that's allowed. If there's too much tolerance or variability, nuts and bolts will unscrew on their own. If they're well made, they'll stay connected as they should. And so we determine the amount of imperfection or really erroneous conclusions that we are willing to live with. And you can see some of the memes continued here. So if drawing a conclusion 5 times out of 100 is okay, an imperfect solution, imperfect conclusion, if 5 times imperfect out of 100 is okay, then we're going to call that p equal 0.05, and we're always going to aim to be p less than 0.05, a probability of being wrong by random chance alone less than 5% of the time. Let me say that again. That less than 5% of the time, the differences are due to random chance, and we think the differences are so large, so whopping, that it's just not random chance alone, but it's random chance plus some effect of the independent variable. Now, maybe that's too much error. Maybe we don't want to make 5 errors out of 100. Maybe we're really okay making only 1 error or less than that out of 100. We can lower the p-value. So pretty much the uppermost p-value is 0.05. It's pretty rare to see us go above that in psychology. But if we want fewer error or fewer erroneous conclusions, we can lower the p-value from 0.05 to 0.01 or to 0.005 or to 0.001. So if only 1 time out of 100 is okay, then we're looking at p less than 0.01. Now, by the way, in medical research, especially if you're dealing with the side effects of drugs and human beings and things that could happen, sometimes p levels are 0.000001 because the chance of error might mean someone dies in medical research. And so we want that probability to be extremely low. In terms of psychological conclusions about variables and how they're related or how there are group differences, that's typically not a life or death situation in p-values and hypothesis testing. And so we're typically okay with p less than 0.05. But if we want a little bit more stringent conclusions, be a little bit less conservative in drawing conclusions, we could lower that to p less than 0.01. So we have a name for this idea. We're going to call this the alpha level. So the amount of error we are willing to tolerate in drawing that conclusion, although sometimes it might be erroneous, is 5% or 0.05 or a nickel out of a dollar. It's the alpha level. And you can see the Greek lowercase a there at the end of that third bulleted sentence. And so alpha equals 0.05 means that that's going to be the criterion by which we're going to accept or reject the null hypothesis. And odds are you encountered this in your statistical methods class that you probably took before the research methods course. That is to say, you might have used p-values from an SPSS printout, or maybe you used a critical values table in the back of a textbook or on a website. And so those gave you those critical values for the region of acceptance and region of rejection and all that good stuff. So that significance level is called a p-value. It's called an alpha level. The standard typical default is 0.05. We have another name for that whole concept as well, that conceptual family, and that's called a type 1 error. So the probability of a type 1 error occurring is 0.05, meaning that in a type 1 error is that when we reject the null hypothesis when we should have accepted the null hypothesis. Now that gets confusing for students. So hang on to it for a minute because I think I've got an example coming up that's really going to make that clear. I know it sounds kind of backwards. We reject when we should have accepted. Well, if we should have accepted, why didn't we? How come we didn't know to reject? And again, I think I've got a pretty good comparison with how the criminal justice system works. I think you'll be able to wrap your head around. And I'm coming up to that in a moment. We're going to call it the truth table when we get to it. So just to recap, that type 1 error in psychological research, by the way, in all hypothesis testing research, type 1 error, we reject the null hypothesis when we should have accepted the null hypothesis. And by the way, I do think this is one of those things that, just like independent variable, dependent variable, that psych majors at some point have just sit down and memorize it so they know it without getting confused by it. Type 1 error is when you reject when you should accept the null hypothesis. I'm going to say it a couple different ways so you can wrap your head around it. We thought the independent variable had an effect, but it didn't. I thought my intervention, my treatment worked, but in fact it did not. So I concluded it did, but in fact I made a type 1 error. I thought there was a difference between the groups, but there wasn't. So I thought my GRE test prep course worked, but it didn't. I thought my lectures were brilliant, but they weren't. Oh, that one hurts, I gotta tell you. So a type 1 error, we thought something happened, but it didn't. We rejected the null. We should have accepted the null. We thought our independent variable was meaningful and working and effective and efficient, but in fact it wasn't. We decide as researchers ahead of time how stringent to be with those types of errors. That is, we set the alpha level with the general notion that the highest it can be is zero point zero 0.05, but you can go lower. And we talked about that just a couple of screens ago. And typically speaking, the default value is that we accept the possibility that 5 times out of 100, which is the exact same thing as saying p equal 0.05, that chance was operating and nothing else. Even though we thought it was chance plus the independent variable manipulation, it was really chance alone and probably because we had non-equivalent groups. So if you saw a type 1 error, clearly you saw a type 2 error coming. And again, I love the continuation of the Mark Wahlberg research meme there you see in the corner. So a type 2 error, we accept the null when we should have rejected it. We accept the null when we should have rejected it. Or we say the independent variable had no effect when it really did have an effect. This is a bummer of a conclusion. So we said, no, the treatment didn't work, but it really did. But other stuff came into play where there was an error and we drew an inappropriate or a wrong conclusion. We conclude no differences exist even though differences truly do exist. And sometimes I'll have students ask me, so what's worse, having a type 1 error and a type 2 error? I'm really not quite sure if there's a definitive answer to that. I can tell you that most researchers in psychology concentrate more on the type 1 than the type 2 error because we have this bias to reject, and so we really don't want to reject when we should be accepting. Let me try to give you a couple examples here really quickly. So for a type 1 error, that might be like saying a snake oil salesperson, I've got this miracle drug and it'll cure cancer. So I'm peddling it. It's usually on the internet. Maybe it's an infomercial late at night. I've got this new stuff. It's going to cure cancer, but it really doesn't. That's a type 1 error. I say something works and it doesn't. A type 2 error would be a cancer researcher's worked in a lab, his or her lab for 30 years. They're retiring. They hold a press conference, and that researcher reluctantly says to the camera, I'm so sorry, I've devoted my life to the cure for cancer, and I've been unable to find it. Yet the cure for cancer actually exists in the laboratory. So it's there, but it wasn't found. So what's worse, to find something that isn't there or to not find something that should be found? I think they're both bad mistakes. They're both negative. We didn't really succeed in the scientific enterprise. And so that's why, hopefully it makes kind of sense and a little bit funny. The meme type 2 error girl, I'm the best you've never had, because we say that the null hypothesis, we accept the null hypothesis when we should have rejected the null hypothesis. We say there's nothing going on, but really there's something going on. So that's the type 1, type 2 error. Now, type 1 error gets the symbol alpha, the Greek lowercase alpha. Type 2 error gets the Greek lowercase symbol beta. You can see it here at the screen at the end of that first bullet. And so it kind of looks like a bee with a little bit of a tail on it. The beta is usually not really under direct control by researchers. It's kind of part of the process, and it is related to type 1 errors. We don't normally control it directly. We don't normally talk about it in publications. We can go into greater detail about it, but I would actually save that one either for an advanced research methods or graduate school, quite honestly, because you could get into it, but it's probably beyond the scope of what we need to at our level for now. So we really don't control it directly. We control it indirectly. I'll mention this a little bit more at the end of this screencast. Okay, so this is a little bit of a long-winded example. I think it's worth it. It's hard for students sometimes to wrap their head around, well, we accepted, but we should have rejected, or we rejected the no, but we should have accepted. Well, if we know we should have, why didn't we? Well, sometimes you've got to make a decision based on the best evidence available. And I think a nice parallel to that is what we see in the criminal justice system in the United States with regard to juries making a verdict of guilty or not guilty. And so let me walk you through this, because I think the parallels will be emerging clearly for you. So in the United States, if it's a criminal trial, a jury sits in judgment and will, at the end of the trial, make a decision whether a person is guilty or not guilty. It's a little bit more complicated than that, but let me have the simplification for the sake of this example. So, and by the way, notice that it's not guilty or innocent. Declaring someone innocent is not the same as declaring them not guilty. And we can circle back to that one if you'd like to in class. So I got to make a decision. So if I'm sitting on a jury, I'm living in the columns there. I'm either going to say guilty or not guilty. Now, in reality, in the true state of reality, which I am not privy to, the truth with a capital T, I'm not going to know that if I'm sitting on a jury. But in reality, someone is either innocent or they're guilty, right? I mean, O.J. Simpson, depending on whatever you think, either he did do it or he didn't do it. Now, a jury had to make a decision. Juries live in the columns, but reality resides in the rows. Okay? And so we've got this little 2 by 2 matrix here. And so when a jury says you're guilty, but the person is innocent, oh, that's a terrible mistake. That's a travesty of justice. And sometimes we discover this. Actually, you've probably heard of the Innocence Project, and they take on these folks who have been accused of crimes, they've been in jail for 20 years, and sometimes DNA testing can help prove their innocence or help at least demonstrate their innocence. And so the jury had to make a decision, that's the column, but maybe there's sometimes people really are innocent. Now, sometimes we get it right. Sometimes the jury says you're not guilty, and in fact, the person's truly innocent. That's a correct decision. We like living in that square right there. Sometimes the jury declares you guilty, and you are guilty. Okay, well, that's a correct decision. And then finally, you can see where we're going with this. The jury declares you to be not guilty, but in fact, you are guilty. That's also a terrible mistake, and you got away with it. So think about the one diagonal there from the upper left to lower right. Those are both mistakes, and they're both pretty bad. One's a type 1 error, by the way. One's a type 2 error. Hopefully you can connect that. If not, I'm about to connect that for you. So which is worse? A person who is innocent being sent to jail, or a person who is guilty getting to go free? They're both pretty bad mistakes that we'd like to avoid. We want to live in the alternative diagonal, that starts in the lower left and goes to the upper right, the correct decision diagonal. We'd like to get it right. But I think you can understand, we found them not guilty, but we should have found them innocent. Well, you don't know that at the time, but you got to make a decision. It's the exact same thing for researchers. I don't know, I'm not privy to the true state of affairs or reality at the time I'm testing my hypothesis, but I got to make a decision, accept or reject. So if you can grasp this, what you see on the screen here, this truth table, this example from criminal justice, then guess what? You can also grasp this notion in psychology with regard to accepting and rejecting the null hypothesis, type 1 and type 2 errors. So let's put it all together. So I'm a researcher, I'm an investigator, I got to make a decision. Either I'm going to reject the null or accept the null. I'm going to do my hypothesis testing. I'm going to run my statistical outcomes, my analyses, and I'm either going to decide to reject the null or accept the null. Now, I'm not privy to the true state of affairs. I'm not privy to reality. I have to make a decision. I live in the columns. Reality resides in the rows. All right. So either in reality the null is true or the null is false. I'm not going to ever know that. So either the null is true. If the null is true, that means there's nothing going on. There's no difference, no association. If the null is false, that means there is something going on. There is an association, relationship, or difference between the groups. All right. So let's put the same 2 by 2 matrix together, just like we did for the jurisprudence example. So if I reject the null is true. Remember, the null is true means there's nothing going on, but I reject the null and I say there's something going on. There is something there, but there really isn't. That's a type 1 error. We label that probability as alpha, and we set the alpha to the significance level, which is 0.05. So that's a mistake. I said there's something there, but there really isn't anything going on there. Moving across now, sometimes I say there's nothing going on, and there really is nothing going on. That's a correct decision. The probability of that is 1 minus alpha, or 0.95. Okay? All right, I think you see the direction that we're going. Sometimes I reject the null, and the null indeed is false. Okay, something's going on there. There's a difference between the groups, and by golly, sometimes as an investigator, I do find a difference between the groups when it actually does exist. That's called a correct decision. That's going to be 1 minus beta. Remember I told you in a prior screen, beta is 0.20. You're going to see that in a minute, that final box there. And by the way, there's a name for that box. There's a name for that probability. That's called power. And I'll kind of give you a quick preview. Power is the ability to reject the null hypothesis when the null hypothesis should be rejected. So that's like saying power is when you make a decision in the reject null column when the null is false column actually is the true state of affairs in reality. And we'll come back to that notion of power here in a minute. Let's finish off the table. Sometimes I reject the null, but the null is false. So I'm sorry, I said that wrong. So let's finish off the table. So sometimes you accept the null, but the null is false. When the null is false, there's really something going on. There really is a difference. But sometimes I say, oops, there is no difference. There's nothing going on. I failed to reject. I accepted the null. That's a type 2 error. A type 2 error is accepting the null when you should have rejected the null. That's the same thing as saying, I don't have a cure for cancer, yet it really does exist in the laboratory. That's a pretty bad error as well. The probability, that's called beta. Beta is set at 0.20, usually by default. So power is 1 minus beta, which is 0.80. And that's the truth table. So I think if you can wrap your head around the innocent, guilty, sometimes the jury makes a correct decision, sometimes they make an error, there's different kinds of errors, then that's exactly how that maps onto this chart right here. We've given the errors labels, type 1 and type 2. The other diagonal are the correct decisions. So let me circle back to power like I promised I would. So again, this is like the word significant in that it has special meaning. So when we do a powerful study, we're not talking about phenomenal cosmic power, it'd be a living space. We're not talking about that kind of power. We're not talking about electrical power. We're talking about the probability of rejecting the null when the null should be rejected. The probability should be power is the probability of finding something when something's there to be found. And so, in fact, you can do something called the power analysis, again, another Mark Wahlberg research meme, that'll actually tell you how many participants that you need to have the best chance at finding a statistical significance. That is, being able to reject when you should reject. So again, just another way to wrap your head around it for power, finding something when there's something there to be found. So I just want to kind of close out with a couple of screens here about ways to increase power because we want to do powerful studies. If we believe our intervention is going to have an effect, we believe there's a difference between the groups or relationship between the variables, then we want to give ourselves the best chance at doing a powerful study. So again, one last Mark Wahlberg research meme for you here. So what are some of the ways to increase power? You could use parametric statistics. That means using data, your dependent variable data, which are based on interval and ratio scale numbers. So interval and ratio scale numbers are parametric statistics. Non-parametric statistics are applied to nominal and ordinal scale numbers. And we talked about those concepts in that scale of measurements screencast earlier in the semester. Another way to assure power, or at least the best power you can get, is to make sure the statistical assumptions are met. In your in your statistical methods class, you probably talked about, normal distribution and violations. And so if the standard deviations are too far off on a two-sample t-test, you talked about violations of the assumptions of normality and things like that. And so statistics are only as good as the data they're applied to. And so if you're misusing a statistic, then you're probably violating an assumption, which means you're actually lowering your power. You can set a higher alpha level, understanding that we don't normally go above 0.05 for alpha. And so let's say that you started off your study and you set ahead of the game a priori. You said, I'm going to set alpha at 0.01. You come along later and you go, I want to increase my power. You could raise that 0.01 alpha to 0.05 alpha, but you can't go over 0.05. So again, going from a 0.01 to a 0.05 means you're going to be rejecting the null more often. It does have a risk of enhanced type 1 error, but it does give you a chance to find something if something's there to be found. It increases that chance. A greater n. Sometimes it's about the sample size. And so if you remember from those critical value tables in the back of a textbook, you might remember that the more observations or degrees of freedom that you had in the table, the lower the value, the t value, the r value, the chi-square, whatever, the f value, the z-score it took to reject the null hypothesis. And so these are just one subset of ways to increase power. Also using equal ends. If you're doing a study that involves Republicans, Democrats, and independents, it's going to be better to have equal numbers of those rather than 30 Republicans, 10 Democrats, and 2 independents. And so equal ends will give your statistical heft a little bit better chance at finding something if there's something there to be found. Just to kind of close this out, other ways to increase power, to the extent you can control it, less variability. So for instance, that might mean switching to a within groups design or a pre-test, post-test repeated measures design if plausible, as compared to a between groups design. If you can reduce the variability, that's good in terms of increasing power. Oops, I just did the spoiler alert. I just talked ahead of the game. So within groups design is actually one great way to have less variability. And there's other screening ways that you could have multiple groups to be compared to one another with less variability. Look for those large whopping differences. Let me say it more colloquially. It's easier to find a pitchfork in a haystack than it is a needle in a haystack. Sometimes differences are small and subtle and nuanced, and those are going to be harder to find and take greater numbers of people in a more powerful study. If you're looking for a big whopping effect that's obvious and happens all the time, that's much easier to find. That's going to have greater power in that study when you're looking for differences that you expect or relationships that you expect to be large. And finally, improve the measure. We are only as good as our measurement devices. So sometimes it's not about the independent variable. It could be about the dependent variable. And so making sure the dependent variable is as finite and as refined as it can be If it's a good measure, it gives us a better chance at finding a difference. Think of it this way. If you were measuring someone's height, you'd rather use a yardstick that was stable or a tape measure as compared to a rubber tape measure, let's say, that it might be more variable. And you might stretch it, you might get wrong, or you might compress it and get the wrong measurement. And so we're only as good as our measurement devices. Sometimes improving the validity of the dependent variable measure might be a great way to increase power. Let me wrap up this longer than normal screencast with a couple other really key ideas, and then I promise we'll wrap it up. We may not go into it so deeply into our research methods class, but it's one of these things that you should know about that really, if you go on in psychology, you're trying to publish in journals, you really should be aware of, and that there's this notion called effect size. And there's two ways to think about it. There's a statistical significance and practical significance. And statistical significance is everything we've talked about up until now. That is, do we accept or reject the null hypothesis? P equals 0.05. We want to have P less than 0.05 to reject the null. Large n's can unduly make it easier to reject the null. Again, that example in the critical values table. However, sometimes that's kind of an artifact or that's an artificial finding. So there's a whole separate other measure called effect size, and there are different effect size statistics for different types of analyses, different statistical situations. But effect size tries to get this practical significance. So just because it was statistically significant, does this really mean anything? And I think I've got a couple of examples here for you. And so I like that third bullet here on the screen, right ahead of the Mark Wahlberg meme. For example, with an n of 1,000 of correlation of 0.052 is statistically significant. However, I wouldn't make any policy determination or any changes to a program or the world we live in with a correlation of 0.05. That is a small infinitesimal correlation. It's nearing zero, which means there's no relationship. So even though technically speaking, it's statistically significant, practically speaking, is a very small effect size. And that's the way that we would use that language together. So you can have a separate effect size calculation. And in fact, if you were to go on from this course and publish the results of your study that we're going to be doing together, you would probably be asked to have some sort of measure and statistic that depicts effect size. So just to give you one quick example, Cohen's D can be used to look at two different groups, two mean values. So if you had males and females or treatment and control, whatever, you could calculate Cohen's D. That would be a number that you would figure out from 0 to upper infinity. And you can see small, medium, and large. It can go over 1, by the way. So a small effect size is the D of 0.20. And he has figured this out and published it, in 1988. And others have followed up on this. And so it's just another way of demonstrating, in combination with significance level, is this a practical effect? Is this something that's really beefy and meaningful? Or is this just an anomaly of having a huge N, a large number of participants? All right, so that's going to wrap it up for us. That's the screencast about hypothesis testing.